So I will start just introducing a little bit who we are. SiPearl is the company that is trying to build the European high-performance, low-power microprocessor to equip future supercomputers. We've been incorporated in 2019, funded mostly by the European Union. And we are aiming at building processors taking using the Arm architecture, which is energy efficient and powerful to build HPC supercomputers. And so the financing was more than 100 million euros from partners such as Arm, Eviden, or the European Union. And we are partners with most of the companies of the ecosystem to integrate their solutions and ours. The first manufacturers that will be the targets of the companies to provide the processor, sorry, will be the Euro HPC systems, such as Jupiter, which is being built in Jülich. So we have several seats in Europe currently and are increasing our headcount. We are more than 200 now. So I'm based in Grenoble. I skipped the slide with my presentation. So I'm based in Grenoble. I used to work with CEA or INRIA on HPC benchmarking, and I'm now part of the HPC benchmark team in SiPearl. So we are trying to improve the ecosystem, make codes work on our platforms, to predict the performance of the code on our platforms and improve that. So the platform that we are currently building is RIA-1. It's an HPC microprocessor with 80 new version 1 cores from Arm with SVE units and HBM memory on board. So I will not enter the details of that and switch directly to the core of the presentation. So why I will explain later why we will use ARM-PL, but what is Arm Performance Libraries? These are the equivalents of oneMKL, but for Arm platform. Basically, it's a set of mathematical libraries optimized for the platform with vectorization, such as SVE or Neon support, and also OpenMP, obviously. So they have pretty much the same domains as oneMKL, so the BLAS interface, LAPACK interface, FFT, sparse linear algebra is supported as well, RNG also, and they provide also optimized and vectorized math and string libraries. So these standalone versions are available on the website with 4 different compilers and also for different platforms. So they support even macOS or Microsoft Windows now. So why did we add a backend to oneMath for ARM-PL? Our goal is to provide a good ecosystem and a good support for most of the codes from the HPC community using our processors, and even with CPU or GPUs targets. So for this, in this case, it meant most of the cycle codes that we wanted to port, and also some other targets were not yet compatible, and oneMath was one way of bringing compatibility to our processors, while keeping good performance portability as well. Reading recently the minutes of the last calls, I saw that actually the ARM processor plus GPU targets was already tested by Durham University, which is great. We didn't try it yet internally. It should be done soon, but we are still setting up the platforms for that. And there was no CPU target for ARM processors. But the cycle compilers were already working, and some backends were already available on ARM. So OpenDPCPP already had a backend, which was the host backend. They removed it at some point. But now another one is back with native CPU backend, so it works as well on ARM. And there is also POCL, the OpenCL backend, open source. So this was tested and works well with our platforms. And adaptive CPP also works pretty well with the OMP backend. So this work was started quite a long while ago. It started as an internship for one of my colleagues. And due to some internal processes taking a long while to be set up, we couldn't upstream code until recently. Now these little issues have been fixed, and we can now start upstreaming our work to the community. So that's why we opened the pull request this last month. No. Okay. So the first to be ported and to be contributed was the Blast backend. So it meant for it to work to first add the support of the Arch64 CPUs in the code, which was quite easy. The in ARMPL and Netlib backends were added at the same time. So Netlib was already present, but it was not activated for Arch64 CPUs. As ARMPL uses CBLAS interface, most of the codes were so straightforward to port. It was the same as in Netlib backend. Other extensions from the MKL are supported in ARMPL, so plenty of calls are the same. So the oneMath add and the such were also added in the extensions. The batch call were also added and implemented with loops when no direct support was already present in ARMPL, but some calls are already batched in ARMPL. So we also did quite a lot of tests on one feature in ARMPL, which is interleaved batch calls. Instead of putting the matrices next to each other for small batch calls of BLAS, they provide a way of interleaving the matrices and adding the first element of each matrix, then the second element, then the third element, and applying the operations on that. So it improves vectorization quite a lot and can provide a nice performance boost. Sadly, it was not really a good fit for oneMath because the need to interleave and de-interleave the matrices was coming in the way of the call, and it was either we do it every time we have a call to a matrix, and it adds a lot of time, or we don't do it. So we decided not to integrate this feature in the backend in the end. We kept some bits, and we can still go to it at some point if needed. But for now, it was put on the side. In the process, we found and opened some issues on oneMath. They were fixed quite quickly thanks to the community, and so I put some tickets. We also found some issues in ARMPL itself. So we discussed with ARM quite a lot to improve and fix some issues. So version after version, they removed the problematic calls and fixed the issues. So this means that now most of the backend is functional. Every test is passing. Some are skipped, like the only calls that are not supported are oneMath add 2, oneMath copy 2, and some batch calls, but it's just small calls that are not in ARMPL that are in oneMKL, but 95% of the backend is supported. So this took around 2 months to do for the Blast backend to be fully integrated. So the PR was submitted last month and thankfully integrated quite quickly. So thanks to you. On the LAPAC side, so this was also done a few years ago, and that was dropped quite quickly. So it was revived last month by me, and I started again from scratch almost. The Netlib backend was not available for this interface yet. It uses the same LAPAKey interface as ARMPL does. So actually, from the ARMPL backend, adding the Netlib backend could be done quite easily. For the calls LAPAK has two different LAPAK has like how do you say? There are two phases. First phase is to query the interface to ask how many scratchpad size will be needed. So this is done using the LAPAKey work functions, and they don't match exactly the interface of oneMath, because oneMath is mostly using the same calls that probably CU LAPAK from CUDA and other implementers did with a single work array, while the oneMath, the LAPAKey interface allows several work arrays for some functions. So some functions will actually return 3 different sizes with 3 different work arrays to implement, to allocate, while the oneMath only wants one. So for these calls for now, I didn't use the scratchpad at all. It is done internally at each call, which is suboptimal, but I didn't see a good solution to this small problem. Anyway, it only adds a little overhead at each call to allocate the arrays. Support for batch call was not added also. It's not supported in RMPL, so they didn't add any batch call in RMPL, so it will need to be loops over every single call, and I didn't do that yet. It could be added if there is people wanted. 100% of the tests are reported as passing, which is actually an issue. I will talk about that later. It means that actually the skipped test, like I said, batch code are not supported, but they still report that they are passing. So that's not good, but a fix is coming. And the PR was submitted during the last week, and it was merged yesterday. So thanks again for the quick validation and the quick integration in the project. Third backend that was added was RNG, so the random number generators. RMPL has released an open source library called OpenRNG, which aims to be a drop-in replacement for Intel VSL library for the random number generation part. And it's included in RMPL as well in the release. Several generators and distributions are implemented. Most of them are already in oneMKL as well. And the fact that it's using exactly the same interface as Intel's VSL says that it was quite easy for the implementation. It means that pretty much it's the same backend as oneMKLs. Some calls are supported, some calls are not supported, but there are just small differences. So I added the two MRG and Philox generators, and the other backends already added. I don't know if that more backends are planned to be supported, more generators are planned to be supported, but they are probably already available in RMPL. There is a small issue with some tests that started failing, and when I found out it was actually an issue in OpenRNG with one generator that is not working as expected with negative lower bounds. So I reported the issue to Arm, and they are currently working on it. So it will probably be fixed by next version. So same thing, the PR was submitted last week and is being discussed recently. And so in this work, we found a few issues in oneMath. So like I said, the first two ones were reported a while ago and fixed by the community. First issue was a C blast symbol issue when trying to compare with reference blast, which meant that actually the blast library was testing against itself, or just testing netlib against netlib instead of testing both. So this was reported and fixed. Also, some issues with CS route and ZD route were found. And in the LAPAC, backend, two issues were identified. So like I said, the skipped test being reported as success is not consistent with the other backends. So I added what was necessary to add the skipped status to test. This is still being internally reviewed on our side, and it will be upstreamed soon. Other issue was that the same issue as blast was identified, blast symbols was identified with LAPACI. The issue is netlib's implementation that is used as the default the reference implementation uses the LAPACI symbols, and RMPL will also use the LAPACI symbols. And if we link against the libraries, they will use the same symbol, and only one of the libraries will be tested actually against itself. So the fix that was done in BLAS at the time was to DL open the symbols from the reference implementation only when needed in order to be sure that it was actually using the right function. So I did the same for the LAPAC the LAPAC backend. So same thing, a PR is ready and it's pending internal review, but it should be soon landing in oneMath. So why did we want to port things, and what are our use case for that? So some of the codes we are trying, we are testing and benchmarking are using oneMKL interfaces, oneMKL directly, and using oneMath interfaces instead. It could be used as a drop-in replacement and add immediate portability and good performance portability also to the code. So that was one of the aims. For instance, the big DFT code that is being developed in CEA in France, which is an Abini DFT code using wavelets, is considering replacing some of its code paths that are BLAS, MKE, GPU using OpenCL or CUDA or things, and they have multiple code paths to maintain separately. And if they could have only one cycle and oneMath code path, ensuring portability to other platform, to all of the platforms, it would be a great win for them. They will be really welcome having only one code path to maintain. So they are working with Intel on that to bring cycle to their platform, and it also means that in order to support, in order to work on ARM platforms, that we need a backend for that. Then we need backends for that. So that will mean also not only adding BLAS, but also adding FFT backend, so the DFT backend. So this means that we will probably look into the future to add the DFT backend as well to oneMath for ARM processors. Also, some experiments were done because the cycle layer allows to play with sub-devices. And for instance, you can split your one device or two devices into separate sub-devices and say, okay, this is an accelerator, this is a host, and what is the performance of my code in this setup with one small CPU playing the host and one bigger CPU playing the accelerator, for instance, etc., etc. There is no product in mind for that, but it's still an interesting way of testing, and so there are some interest in this experiment. And also to try the interleaved batch calls and other strategies of doing the call. So it was a quite nice way of doing our tests. Next, I will just show a little performance test I was doing actually this morning, using DGEM and the backends. So what I did was try on 3 different platforms and compare the version with direct CBLAS call. For Intel, the cycle, the OpenMKL cycle call, and compare it to the oneMath call, so using MKL for the Intel part and the oneMath plus ARMPL for the ARM processors. So the blue one are the Sapphire Rapid processors that we tried using 40 cores. So single core is up and the full socket is down. And the thing is, BLAS and cycle and native cycle, like native oneMKL call, was performing roughly the same. But there is a slight drop in performance for oneMath plus MKL code. I'm still wondering and trying to find the issue here. I think there are some parasite threads that might have been launched and that are taking some time. It can be seen in the single core where we pin the thing to a single core, and the drop in performance would mean that maybe there are two threads competing in this core, in this setup. So the drop in performance was not really expected for this. But for the ARM platforms, so there are the Ampere in red and the NVIDIA Grace in green. It's actually the opposite. The direct BLAS call is somewhat slower than the oneMath plus ARMPL call. They are both using the same DGEM call inside. So I still don't know exactly why there would be any difference at all, and why it would be in this direction. So the same thing, I'm a bit puzzled by these results, but they were quite reproducible, and I'm still I will check into it soon. But this means that performance is roughly the native performance of the calls of the same calls using BLAS. So this is just DGEM, just the simplest one, but this means that still we don't see a drop in instruction rate using oneMath. So this is a good result still. So we have to check also with calls that are more memory intensive, obviously, but we didn't see in our test bad performance. In conclusion, so sorry I didn't finish because I thought the call was 1 hour later. So the BLAS, LAPACK, and RNG domains are available for Arch platforms in oneMath. Performance seems to be close to the native performance of the calls. DFT will be probably the next target. We need to map it to the FFTW interface. I don't think any backend has done such things yet, so I will have to check how I can do that. And maybe sparse BLAS would be also a good target for the next part. So I think I finished, and thank you for listening. And if you have any question.
This is great, Augustine. Just one small thing. On the last slide, you mentioned FFTW. I think oneMPL backend has some header files that enable the FFTW interfaces for the FFT functionality in that backend. But yeah, I have to check if works with oneMath. I don't remember the top of my head right
So I can't hear you very well, but you say that there is already a FFTW in some backends?
in one MKL backend. So you
In
can check
OneMKL?
the yeah, you can check the
Yeah,
header file.
OneMKL, I think they use DFTI interface or something like that. Um, and they provide FFTW wrappers around
Yes,
these
correct.
DFT calls, I think. But it would be the other way around this time. So it will be wrapping FFTW calls in DFT. But I will check these interfaces. I think they have code files, code source already available inside the released oneMKL for that because they allow to do your own wrappers. And I think
Right.
it will be a good starting point. Yes,
Cool.
at least to see how it works the other way around.
Yeah, makes sense. Thank you.
Yes.
Hey, thanks for all the work. It looks great. So I'm Chris from Arm, and thanks for all the little reports of bugs that you've passed through. They've been great, and I think we've got them just about all fixed now, barring the RNG one, which should be upstream hopefully by the end of next month is what we're looking for that one.
Right.
One question I was going to ask. So your performance graph at the end, where you
Yes.
showed the better results for the sickle, were you actually pinning threads on the OpenMP version yourself, and was sickle?
Yeah, I was trying to do it as at best, and sometimes I noticed that it was not obeying everything I was asking. But for the single core, it was definitely pinned. For the 70 the full socket, things were a bit more hectic. But the same. But yes, I think one of the issue is also that one for the SiPearl rapid test uh, using oneMath, I couldn't find the right environment variables to give to say okay use pin the code or pin the process or use this amount of processes instead of taking all the node. It was always a little battle to find the correct setup. MKL using CBLAS and Cycle and the oneMKL was respecting the environment variables like MKL num thread or MP num thread. While using oneMath, it was just no, I'll take what I find. So there's a little maybe usability tricks to find here to tell the user how to express the number of cores they want and how to run it. Using task set, numactl, and such helped to reduce to force the code to compare to obey, but it was a bit more difficult. So the fact that in the ARM platform it behaves better is a bit weird because the oh shit, sorry, I'm step
Yeah,
clicking.
and that's what makes me think it's something like.
Yeah, I think there's something like that because when I check inside, it's actually using the same code path. It's going to the same reference implementation in RMPL to the same DGM. So I think the issue is mostly pinning and some somehow oneMath doing things better. Maybe actually the pinning doesn't help, and the thing that extra threads that are trying to handle to handle the computation are being disruptive. So I don't know. Maybe it's something like that. But it's in the end, it's only a few percent of difference. but still there was some difference.
Yeah, and I guess my next question might be one for Sarah or team there. You talked about the fact that there weren't quite so many batched routines in RMPL compared to oneMKL. So you mentioned the interleave batch functions. There's
Yes.
also a set of batch gems. I don't know if you noticed those called dgem underscore batch, for example,
Yes.
which literally does a very plain one. But we've never gone and done many more of those functions because we've never had users wanting that. So
Yeah, I think that's why we use the ones that are available. I think the DGEM batch is used in the
yeah,
in the backend in the interface we submitted. Not the interleave ones, but which was quite interesting to play with. But yes, indeed,
yeah.
if there's
But
no users willing to use
well,
them, it's
I guess that's one of the questions for Sarah and others. If you know of people wanting these applications, needing those, or the oneMath add to and copy to functions, we've certainly had nobody come to us asking for int8 or bfloat 16 versions of
and I
any
think
branch.
it's pretty much the same for 90% of the LAPAC functions that are
Well,
quite
exactly.
a lot.
So,
Yeah.
in terms of what work is necessary coming out of applications, people using oneMath, clearly Intel decided to put them in for some reason. So, if anybody has any useful data to share, that I'd be very interested in getting that. So we could support it potentially in future if there were good use cases. Otherwise, it would stay unsupported for now. And is that a problem for people, I guess, is the question from Arm's point of view. I'm going to take silence to say everybody's happy.
Yeah, a lot of the history of a lot of these functions is so old. It's sometimes hard to know where it came from. But yeah, this is really cool. This is a to me this is like a really big moment in nerdy math library history of you know we got oneMath running on ARM now. It's it's quite a huge uh, set of devices that has opened up to the library.
We had an email actually from one of the CodePlay team that came in yesterday that I've not quite got to the bottom of all the issues they were asking about. One of the things they were talking about was the idea that somebody might want to compile using the oneMath MKL header files and then dynamically link in an RMPL build instead. Do we actually think that's a serious thing that anybody would be doing, as in switching out one library for another at runtime? Because the issue there is inside the MKL header files, they set up a set of enums, and inside RMPL we have a different set of enums doing the same thing. Intel hadn't open sourced those numbers to us, so we didn't feel we could copy the numbers that they'd done, which means that you can't just transfer one enum effectively compiled version to another thing. Feels like a very much an edge case that wouldn't be a problem for most people to me, but if people have experience of where somebody might be wanting to do that, that would be interesting to learn as well.
Sorry, I don't see so you said people would compile against for ARM, but using the Intel MKL, not the oneMKL plus RMPL.
Yes, so if they were to compile against OpenRNG, to be able to run on x86, to use OpenRNG as the
okay on x86.
Yeah.
Whoa, I don't
I
know
think
actually.
it's probably an unlikely use case given that
Yes,
we've not got
for now
optimized.
the backend looks for RMPL, doesn't look for OpenRNG standalone library. I think it could work using you could have a x86 RNG, OpenRNG backend quite easily, I think. But yeah, I don't know if it would be an issue at all with the other using the same interface instead. And if you could do the drop-in replacement by using OpenRNG x86 to replace at runtime the MKL, I think it would still have issues. Some of the API may not be exactly compatible. I'm not sure.
It should all work. We've worked hard to make sure the APIs are the same.
Good. So it could be cool. a nice thing to try. I will stop sharing my screen now. Okay.
I did have one other question. You had mentioned the interleaved batched, and you're right. I don't think we have any oneMath APIs for that. But is that something that you think would be useful to have added to the specification, and then ultimately oneMath project, or?
I don't know if Arm is still working on this. It's maybe Chris can say something, but I think it's really an RMPL thing for now. So that it would mean only one backend would have such support. But if other backends decide to implement the same set of functions, it could be interesting, yes. Because I think the gain is not ARM only. It would be a performance boost for any platform.
Right. Yeah. And I know we have some sort of interleaved batch interleaved stuff in the Intel oneMKL product. I don't know. Similar to what.
It's not dissimilar. We were both doing work with Sandio, I think, and they were the ones. So strangely, it's all taken inspiration from the same places, I guess.
Exactly. Yeah, though I don't know if that's been done much beyond CPUs. Like if any GPUs are doing a similar interleaved, or if it kind of stopped at the with CPUs. But yeah, if it seems like there would be good use cases.
Again, I guess it's a user's interest in the end that drives things. So if users pick the interleave batch and add it to real codes, it could be a good target, yes. But I don't know if there was enough traction on that yet.
Yeah, I think the interesting bit will be to do the sparse bits as we go forward. So, say Hartwig's on. We've got this new sparse standard coming, which feels like the right time probably to do something which is unified between all the products and sits in oneMath and does the right thing, rather than trying to shoehorn these almost similar APIs across the different ones to be the same. Yeah, I think probably hold off on that little bit to try and standardize it, because the standard is coming. I think it's my take on that one.
Well, any other questions, comments from folks?
I'm Biagio from Salerno. Thank you very much for your presentation. It was very interesting. I have a question regarding the code generated for the Grace. So Grace is SV. Did you generate your code? So as far as I understand, you can either generate code that is vector length agnostic or vector length specific. What did you do?
Well,
because
actually,
I know there is a tiny different performance.
As we are using the ARMPL version of the DGM, actually, we are not generating any code for this. We are using the binary version that ARM is providing, and ARM in ARMPL they have a whole decision tree for each call, saying, okay, for this particular one, for this particular platform, we'll use the SV2 version or the SV or the Neon one. It's the this is done inside RMPL. It's not done by me.
Yeah, I think the key bit there is that the interface, the oneMath bit, needs to be pure generic code which will compile and run everywhere.
Yes.
In the same way that on an x86 you wouldn't want to have AVX512 bits if you ended up running on just an old machine with SSE, for instance. And yeah, as we say, inside RMPL there is magic that happens, and whenever I look at those bits of code, I'm terrified. But that's where those decisions are taken as to which things are used in which area.
So it's multi-versionet and not vector length agnostic. So this is what I understand.
It is, well, it is vector length agnostic inside the code, but it is done on a per platform basis. So what happens on a Neoverse V2 core inside a Grace thing might be different to what happens on a Neoverse V2 core inside an AWS Graviton 4 instance, for example, because they've built different chips, they've got different blocking sizes that are needed, different memory speeds. So this is what I'm saying about the magic part of that there's a much wider set of variations that can happen between these cores that we don't want a user to ever have to worry about. And so, for example, a oneMath user should never have to worry about what's going on inside the calls in terms of what architecture it's running on. So it certainly doesn't want to worry about which sort of vectorization is necessary or things like that.
Thank you. Thank you very much.
And I noticed that in my slide, I wrongly stated that Grace is V1 instead of V2, obviously, and I fixed it. Yeah.
Are you happy to share the slides, by the way?
Yes, no problem.
Be great.